Hey, good to see you. In this video, we're going to review concepts for Unit 7. So we're going to look at thermodynamics. So we're going to look at the concepts of temperature, thermal expansion, we'll look at thermal equilibrium problems, and the gas laws as well. Okay, in Unit 7, one of the things you got to be able to do are equilibrium problems. So this is a case where you have two substances, they're at different temperatures, you put them together, and there's going to be a heat exchange until they both reach the same temperature. So let's look at, I don't know, some water here. We're going to take a chunk of steel, and we're going to throw that in. They're going to start off at different temperatures. In this case, let's say the steel is at a higher temperature than the water. It doesn't matter, we could do it the other way too. You could have the water at a higher temperature, the steel would increase in temperature, the water would cool down. It doesn't matter, but in this case, let's just say the steel is at a higher temperature. Well, the first law of thermodynamics tells us that whatever energy the steel loses has to go into the water. It has to be the exact same amount. Energy can't be created or destroyed. So however many joules of energy are lost from the steel, that's how many joules of energy the water can gain. And if these are the only things that are exchanging energy, then that's the only energy that the water actually can get. So that means if we write out equations for each of these things, so let's make that from the steel and write the water over here. So the first law of thermodynamics tells us that the Q right here has to be equal to the Q right here. They have to have the exact same value. But the second law of thermodynamics tells us that energy always goes from high temperature to low temperature. Because the steel starts out at a higher temperature in this case, we have to make sure that when we set up our equations, that substance is losing energy. Because it's losing energy, it has to have a negative Q. So we say the heat lost for the steel, that's what negative Q means, heat lost is equal to the steel's mass times specific heat times its change in temperature. Over here, the heat gained, the energy gained for the water is equal to its mass times its specific heat times its change in temperature. And because of this, we can set these two things equal to each other. But first, we have to do a little bit of manipulation. We have to divide by -1 on each side of this equation. So negative Q minus -1 is Q, and then all of this stuff divided by -1 is negative M times C times delta T. And we have to do that to be able to set these two things equal to each other. So when you write this out, we're really going to be going, okay, the water's mass times the water's specific heat times its change in temperature, which we can call final minus initial. Remember, when we do change, it's always final minus initial, has to be equal to the negative of the mass for the steel times the specific heat of steel times the final minus the initial temperatures for the steel. Now these things right here are all going to be given to you. Those are known quantities. The starting temperature of each object, the mass of each object, and the specific heat you'll look up in a table. What are unknown is here is the final temperature. But we do know that when the point is thermal equilibrium, those two things are going to be exactly the same. They're like terms. So we can solve this equation out. We can plug in the numbers that we have. We can solve this equation out, combine like terms, and solve for the final temperature. Unit 7 equations. We've actually got quite a few equations from Unit 7. So we got 1, 2, 3, 4, 5 different equations from Unit 7. First one, pretty simple. The temperature is equal to the temperature in degrees Celsius plus 273. This is simply just a conversion between Celsius and Kelvin. So the Kelvin temperature, we take the Celsius temperature and add 273. Pretty simple. The next equation, this one right here, We got P1 times V1 over T1 equals P2 times V2 over T2. This is called the combined gas law. The point of this equation is to figure out how these different variables, pressure, volume, and temperature, are going to change in a given situation. In some cases, all three of these things will be changing, and you'll fill in numbers for each one of them. In some cases, something will stay the same. So let's say the volume stays the same. If the volume stays the same, then we know that any volume that we put in on both sides will simply cancel each other out. So the simplest thing is just to put a 1 in for each of those. Some people think about just leaving them out, and that's all right, but just realize you're not putting a 0 in. It's because it's canceling each other out. We can just ignore them multiplying by 1. When you set this up, the best way to solve this problem is to cross multiply. And we can actually even rearrange this in terms of that. So if we cross multiply, we take P1 times V1 times T2, and that is equal to, if we cross multiply this way, T1 times P2 times V2. And that's a way to kind of rearrange it and get that temperature off the bottom. It's really important if the temperature is one of the things that you're solving for, because I've seen that so many times that this is our unknown right here, that people set this up and then they divide the absolute wrong way and get a temperature that doesn't make any sense whatsoever. So be careful about that. You need to cross multiply so that you get that off of the denominator. Next equation right here, change in length is equal to alpha times the original length times the change in temperature. This equation is fairly straightforward. A couple of things. This alpha value, of course, stands for the coefficient of thermal expansion. Basically, it's a value you look up for the type of material you're talking about. So if it's copper, you look up copper's value. If it's steel, you look up steel's value. This is the starting length. The equation tells you the change in length. And you have to be careful about that. If the problem asks you, how long is the object now, or what is the new length of the object, when you do this calculation and you get an answer out, you're just going to get the change in length. And so then you have to add that to the original length. The change in length should be negative if the object is cooling down. It should be positive if the object is heating up, because that's going to tell you whether it gets bigger or smaller. You won't get those wrong as long as you do your change in temperature correctly. Remember, change in anything, in this case temperature, should be the final temperature minus the initial temperature, always. So that if you have something that is cooling down, where the final temperature is bigger than the initial temperature, you'll get a negative answer here, and when you multiply that through, you'll get a negative change in length, which makes sense. Okay, the next equation is the equation for heat. Heat, or change in thermal energy, two terms for the same thing, is equal to the specific heat multiplied by the mass multiplied by the change in temperature. Now, we just talked about how change in temperature always needs to be final minus initial. That's important in this case as well. The mass here, pretty straightforward. The specific heat is another value that you look up out of a table. You have to make sure you choose the right one, though, and don't look at the wrong table. Don't get specific heat confused with heat. This is the energy that is going to be transferred for the object. Now, if this thing is increasing in temperature, Q here should be positive, because the energy input is going to be positive. If the thing is decreasing in temperature, that means energy or heat is flowing out of the object, and Q here should be negative. We generally see this in conjunction with thermal equilibrium problems, where you have two different substances and you set it up as Q equals M times C times TF minus TI. I'm just going to cheat and copy that right over. So I made another table there. But the point is, we have two different substances. One of the substances is going to start at a higher temperature, and so that one has to have a negative Q. And when you start doing these problems, you'll put them together, and the only way you can do that is if you take out that negative sign by multiplying the entire equation by -1. And then the final equation is the one for pressure. Pressure equals force divided by area. Now, a lot of people get confused here because area is measured in meters squared. All that means is meters times meters. And you get that because if you think about taking the area of a rectangle, let's say the area or the lengths here are 2 meters and 1 meter. When you multiply those together, you don't just multiply the numbers, you multiply the units as well, and you get 2 meters times meters, or 2 meters squared. That doesn't mean that you take an area. For example, if I were to give you an area of 10 meters squared, or sometimes we say 10 square meters, that doesn't mean you take 10 and square it before you put it in the equation. No, that's just, that square goes along with the units, not with the whole number. You got to be a little bit careful about that. Also, force here, if we're talking about a solid object sitting on the ground or on the snow or whatever, the force is going to be the weight of the object. And of course, weight equals mass times the acceleration due to gravity. A lot of people forgot that on the test. You have to multiply the mass by 9.8 and then put that into the equation, divide by the total area to figure out what the pressure is. Pressure, of course, is measured in pascals. Also, don't forget how many feet, tires, whatever the object that you're looking for the pressure has, because if a single tire has a certain area and there's 20 tires, well, then you're going to have a much lower pressure because that area is spread out much bigger. And you have to take that into account when you're calculating the area. So you take the area of a single tire and multiply it by how many tires there are to figure out the total area.